So even though it's a short week, we will still have the quiz. There are only 2 weeks left in the semester. So this Thursday we'll have a quiz. And so the usual thing tomorrow, after we go through the homework, we'll have the quiz review. It will be a fairly short in terms of material because obviously we haven't done much beyond the test. And then in some ways nothing next week because the third test is on the day of the final. And I forgot to look up when our final is scheduled for. So there isn't a final, there's just the third test. Again, the 23rd, there you go. Again, when I looked this morning, the test had not been graded. Sorry about that. But as usual, if you only submitted it to me, then if you send me an email, I'll send you back your graded test. The answers are on Blackboard. This time there are 3 versions, so just make sure you're looking at the correct one. Okay. All right, so we have started 3.11. So I'll remind you of the formula we get, which turns out to be fairly straightforward once you have the formula. We'll do one example, and because we have the test, I didn't ask you to look at the homework yet, so I'll just do the one example, and then obviously we'll do some of the homework tomorrow. And then you'll have it on the review and so on. And then we'll get into chapter 4, which is, we'll talk about it when we getting into vector fields. So actually some more applications. So 3.11. is surface area. And again, remember the idea here is we have a 2-dimensional surface in 3 dimensions, and we want to find what's the area of that thing. And we found, and I'll remind you where it comes from, is that, and then we'll do an example. And there are 2 forms of it. Second one, I'm putting dy dx, but of course it can be either or. So D is we're looking at a surface in 3 space over a region D. And in the first formula, we're assuming that the surface can be parameterized by the vector function r of u v. And remember the idea of this formula is that r of u and r of v are both vectors that are parallel to parallel to the plane. And then if we take the cross product and look at the absolute value, or the magnitude, we know that gives the area of the parallelogram formed by those 2 vectors. So this part is the area of a little piece of it, and then we add it up over all the little pieces over the surface. And then if you think about the really basic parameterization, which I'll talk about in the example, you can see that that becomes the second formula. So for you, I'll pretty much always, for the quiz and the test, I will give you ones where it's already parameterized, so you won't be using the second formula, but the first one, especially because that kind of leads into chapter 4. But in theory, they're about the same thing. As I said, I'll explain with this. So let me do an example. Actually, I think so I can fit it all in one, do it on the next page. So here's the formula. Any questions on this? So let me go to a new page so I can fit the whole problem on it. here is a surface over a rectangular region. And what I'm saying here is you'll notice here basically I can also think of this as our xy. And I'm just letting the two variables be themselves. And so what we're looking at is z is equal to x squared plus y squared, which is just a paraboloid. So we have a paraboloid, the really basic one, just x squared plus y squared, and we want to find the area of that piece of it above x and y, x between 0 and 1 and y between 0 and 2. And this is where we get that second formula. So we use just the really basic parameterization, x and y, the variables as they are, and the third as just the function of the x and y, and you'll see we get the formula for the second one. So for this, what we have to do is we have to take the two partial derivatives. So we get r of u, which obviously is pretty easy, 0, 1, and 2u. Take the partial with respect to v. Again, pretty basic. And so the idea are these are parallel to the tangent plane and tells us how far we're moving along in the u and v direction. We then need the cross product. That's a 2u. That. And so for that I get negative 2u, negative 2v, and 1. So there is the cross product. And in some ways, I don't, unlike what we did before, I don't really care about this vector by itself, because what I'm using is the fact that the area of the little parallelogram is the length of that vector. And here u is going, so v goes from 0 to 2, u goes from 0 to 1. Those could be functions, but usually I would make that a bit more explicit. And then the square root of the, so the length, so the square root of the sum of the squares. I'd at least do the basic arithmetic, which is that is square root of 4u squared plus 4v squared plus 1, but I didn't give myself enough room. And you can do the same thing. As long as you do all the preliminary work, take the derivatives, take the cross product, unless I ask you to do the integral, which I certainly for the quiz, you can leave it like that. And so this is the area of, as I said, the part of the surface, part of the paraboloid above this rectangle. So on the quiz, certainly, I will give you pretty much like here. I'll give you the parameterization. I'll give you the limits. So the two things, as I said, I could make it so one of those is a function, and then you just have to remember that that means that has to be inside integral. And then you take the two partial derivatives, take the cross product, and then remember the magnitude. So any questions on this? Okay. So since it mostly is formula based, I'm just going to do the one example, but as I said, we will do at least a couple of the ones from the homework for tomorrow. So tomorrow you're going to look at this homework. Okay, so the next thing is chapter 4. In some ways, .1 is just an intro. So we're going to go through this fairly quickly. So one is an intro into the ideas that we're going to get in chapter 4, and one is some of the definitions that we'll use. So mostly I will just give you the definitions and do one example, and then wait until we actually use them in later sections to talk about how we use them and so on. So for us, this will be a fairly quick one because it's all kind of getting us into the rest of the chapter. First, let me backtrack a bit. We've been using this for a little bit. So this is a function in vector form or parameterized form. And the idea is this is a point. And with this, we're showing how we move along a path. In this case, 3 dimensions. So we've been doing this for a while. A vector field looks very much the same. In fact, they'll use the same thing except for different variables, and there's no reason really to change the variables. But what I'm showing with the parentheses here is now we're looking at the output not as a point somewhere on the surface. We're thinking of it instead as a vector. And so in some ways, that's the difference between a vector function and a vector field. A vector function, we're looking at the point at a particular value of s and t. In a vector field, we're looking at a particular vector at a particular point, x and y. And so in this chapter, we're going to look at 2 main types of vector fields and kind of bleeding into a few other ones. That's an extraneous mark. So one is either a gravity or a force field. And so this is something where we're in a space and at different points in the space, either gravity is different or there's an electrical current, so there's a force field of some sort. So let me do an example in a second, but notice this will, and I'll say what exactly this is giving us in a second. Yes, so we have a quiz. We have usual quiz on Thursday. So Tomorrow you'll get the review. We'll have a quiz on Thursday. It will have less material than usual, but yes. So we just have the one quiz this week and then the one test on the day of the final. So quiz 4 and test 3. So this will lead to what is called a line integral. And let me make it more specific before I get to the other type. So here's a vector field where this is due to a force. If I start putting in points, I, for example, notice that at 1, 1, it is -1/2, -1/2. If I put in 1, 0, I get -1. So I can start graphing them. So at 0, 0, I get nothing. As I said, at 1, 1, I get the vector pointing that way. If I'm at 1, 1, I get a vector pointing this way. And then kind of so on all the way around. So what I'm getting is at all the different points, I'm getting vectors pointing. And so here you can kind of see what's this in a really simple way represents is I have something at the origin that is pulling on everything outside of it. So some kind of gravity field type thing. And so what I would want to know is suppose I'm in this vector force field and I move along a path. So this is not the vectors, this is the path that I'm going through the force field. I might know what is the integral of the force field while I'm on this path. And in that case, in the basic case where we're looking at force, what we're going to get is the work to move it along that path. So here's the one type. And this is in, as I said, sections 4.2 through 4.4, looking at line integrals. So in the background, I usually think of it as finding the work to move along through a force field, but it can apply to lots of other different types of things. The second type is instead of a force field, is what's called a velocity field. And this will lead to what are called flux integrals in sections 4.5 to 4.7. In a velocity field, when we plug in the point, we get back what is the velocity at that point. And the way I usually think of this in the background is think of it as we have a river, so the water's flowing through, but at any particular point, the velocity vector might be fairly constant. And the velocity field is giving us what is the velocity at all the different points in the river. And in that case, flux integral, which is just another word for flow, and sorry about it's being really great with my writing here, gives the flow through a surface. So imagine on a river, we have an imaginary dam, and I want to know how much water goes through that dam, given the velocity field of the river. Because we have these different things going on, which is if we have a river, it is usually flowing faster in the middle than it is on the banks because the banks slow it down. And if there's obstructions on the base of the river, the bed of the river, or somewhere else because of trees or whatever, then we can have whirlpools and so on. So we can have things moving against the current. We can have things moving up and down. And with all that, we want to know how much of it actually goes through this imaginary dam. And that we're going to get in sections 4.5 to 4.7. And again, I'm using in the background, thinking of it as a river type thing, but again, it corresponds to lots of different cases. So this is what we're getting into chapter 4. Line integrals, which in the background I think of work as we move through a force field, and flux integrals, which I think of the amount of water that goes through a process in a particular time. So the rest of 4.1 is just a few definitions. So I give the definitions, as I said, fairly quickly with just one example, because then we'll really use them in later sections. So when we really use them, I'll remind you of what they are, and then you can see what they're used for. So right now, they're just a tool for now, which don't really mean anything. So the gradient vector field of a regular function, in however many dimensions you want, is just the usual gradient. And that gradient in this case is called a gradient vector field. And that leads to a definition that we'll actually use. A vector field, which is a gradient vector field, so is the gradient of some vector, is called a conservative vector field. In that case, the original function little f is called the potential function of the vector field. So since in some ways this will be what we do in section 4.3, I'm going to go backwards here to do the example. So here's just a typical three-dimensional, three-variable function. I take the gradient in the usual way. as always, you'll tell me if I write something silly, and that, of course, is z cubed. Okay, so that's the gradient. If I call this F, so if this is vector field F, then that vector field is conservative because there is a function whose gradient is equal to it. And pretty easy to make something where that's not true, so it's not conservative. So if I say F is equal to, let's say, xy, xy, go through a simple one, there's no F whose gradient is equal to that. And we'll really do this in 4.3, so I'll just talk about it, because what we would need is some function whose derivative with respect to x is xy. And so that, therefore, we'd have to have something like 1/x squared y. And at the same time, we would need some function whose derivative with respect to y is xy, which means we need the function to be, for example, 1/2xy squared. And those aren't. So there is no function whose gradient is equal to that. And so the idea is ones that are conservative will have some nice properties. It'll become similar to the idea of an antiderivative. So that little f is in some ways sort of an antiderivative of the vector field. This we'll get into in 4.3. When we first use it. More definitions. If a vector field is three-dimensional with however many, here I use F1, F2, and F3 just so you can see this would generalize to as many as you want. And what's called the divergence. Interesting. Right, sorry, being a little weird on me here. This is 4.1. So this is still, as I said, this is kind of the intro. And sometimes it's written this way, which is just a way to remember what it is, which is it's equal to the derivative of the first function with respect to x, plus the derivative of the second function with respect to y, and then plus the derivative of the third function with respect to z, and however many variables there are. An example, if we have a vector field, if I have this, then the divergence of f is just the derivative of the first function with respect to x plus the derivative of the second function with respect to y plus the derivative of the third function with respect to z. And that comes up in 4.6. There's a theorem that shows that this thing will let us do flux integrals in a slightly easier way. So again, it's looking forward. So right now, it doesn't really have any meaning. This is just, here's the definition, it's a tool. So any questions on this? As I said, going through this fairly quickly because we're not going to use it for a little while. Another definition. Given a vector field P, Q, and R, and this one is pretty much always 3 dimensions, which is why I can label P, Q, and R and not have to worry about other ones. What's called the curl of the vector field. Again, kind of as a way of remembering what this gives us, this is just sort of a memorization technique. It's not a big deal. Is again all a memorization thing. Do that, you see, this is saying for the first entry, I'm going to take the derivative of r with respect to y minus the derivative of q with respect to z. And then for the middle term, it's the derivative of r with respect to x minus the derivative of p with respect to z, but then we put the usual negative in front of it, so it flips to e of z minus r of x. For the third term, it is the q with respect to x minus the p with respect to y. And this officially is the curl. Again, as it is right now, that doesn't have any meaning. It's just, this is a tool, and we'll find out in this case in 4.7, I think, 4.6 or 4.7, that this again will allow us to make a flux integral into something that's easier to deal with. Also, we'll see that this part of it, at least, is giving us the summing or showing us whether something is conservative. So it'll come a bit in 4.3. And while I have it here, and then I'll do an example, is because it is useful, there is something that's not officially the curl. So since it has the same thing, it doesn't have the same meaning, but since it looks partially the same, it's given a similar name. So again, for now, just a tool. We'll use it in later sections, and we'll talk about it. I'll talk about what it means when we get to it. But let me just do one of the curls, and then we'll actually start 4.2, where we actually are doing the line integrals, and then we'll do the variations, which we'll start using these tools. So as a quick example, this is this. And let's get this thing that we'll call the curl. And so I know from when I just erased, which I always have to look up, which is why there's the memorization technique from the last one. And so therefore it is, now we just plug in, this is P and Q and R. So therefore it's the derivative of R with respect to Y, which is 2YZ, minus the derivative of Q with respect to Z, and then the derivative of P with respect to Z, which is 0, minus the derivative of R with respect to X, which is also 0, and then derivative of Q with respect to X, and minus the derivative of P with respect to Y. That is what's called the curl. So 4.1 is kind of a weird one. It has this quick intro to what we're doing in chapter 4 and then a few of the definitions. So any quick questions on any of these before we start actually using them? So in some ways, because we're going to start using in the later sections, if you want, you can mostly ignore the homework in 4.1 because we'll really use it in later sections. You should probably read through it quickly just to make sure you know the definitions and know how to use them. So when we do use them, you're a bit more familiar with them, but you don't have to. So first drill section is 4.2, which is line integrals. So given a vector field and a fairly nice curve, is written this way, integral over C, so we're back to a single integral, of f dotted with dr. And in some ways I'm going to wait until we actually do an example, because with the example then you can more explicitly see what this is giving us. But if you go back to what I said before, where line integrals, if we're thinking of this as a force or gravity field, it's giving us work, you can see that this is going to be similar, because we know that work is equal to the dot product of force and distance. And so it makes sense then to define the line integral, which is skimming work, as a dot product. So here's the official definition. And I'll do an example, as I said, which will kind of say what's happening. Here's the definition. We have a vector field, and R is a piecewise regular. So this is what I mean by nice in the first statement, which means that it doesn't have any corners or breaks or anything except at a finite number of points. So piecewise, it's smooth, which means differentiable and so on, of a curve. Then this is what we're getting for this line integral. And as I said, I'm going to do this, start with an example, and then it's easier to see what's going on, and it's easier to explain what's going on. Let me do an actual example. Well, I'll use it in a second, so I'll write it down right before I use it. So given this, find the work So what we're going to do is find the work to move along the curve from 0 to 2, or in particular, let's say from the point 0, 0 to the point 2, 6 along that curve. So the formula is that this is equal to this. So there's the formula again. So what we need is a parameterization. And we can assume, or I can assume, since there isn't a final, that you can do really basic parameterizations, because one parameterization that always works is I can let x equal to just t, just to show that I'm leaving it the same. And then in that case, y, which is x squared plus x, is equal to t squared plus t. And therefore my parameterization is just t squared plus t. So pretty much always is a fairly simple parameterization where you just let one variable be basically itself and then solve in terms of the other variable. So here's my parameterization. And so according to this, we need to do two things. This says we need to plug this parameterization into our vector field. So wherever I see an x, I'm going to put a t. Wherever I see a y, I'm going to put a t squared plus t. So I have 2xy, so 2x y, and then y minus x. Get that. Get that. So that's a function where I plug the parameterization in for x and y. And the other thing I need is what is the derivative of the parameterization. And so this we just take, for the parameterization, just take the derivative one term at a time. So derivative of t is 1. Derivative of t squared plus t is 2t plus 1. And since we're going from x equals 0 to t, 2, that means we're also going for t equals 0 to 2. Since x is just t. And then we're going to get this vector here's the integral. You can see when I take the dot product, I'm just going to get a single integral of the variable t. So let's look at each of the pieces. So let's look at r prime of t. What these two numbers tell us, it says, well, if I move by 1 unit in a t direction, if I change t by 1 unit, then I'm going to move 1 unit in the x direction and 2t plus 1 units in the y direction. So that's giving me how far I'm moving for a change in t. But this one, in some ways, I almost might as well make you do it, just because you can see this is just going to be really easy. But yeah, in general, like usual, I would just have you stop. So this gives us, for a change in t, how far I move along in the x and y direction. And notice this is assuming I'm moving in a linear way. So I'm not curving anymore, since I'm just going over a very short distance. Yeah, I'll do that in a second. So just take the dot product. So in this case, you get 2t cubed plus 2t squared plus 2t cubed plus t squared. So the usual integral thing, this is saying what happens if I change t by a little bit, how far I move in the x and then the y direction. And since it's just a little bit, I'm assuming we're moving along a straight line. Because remember, we're moving in a curve, so we're only in one dimension, so it really is a tangent line. So how far I move if I was, in theory, moving along a line. Oh, how far I move. Oh yeah, that didn't come out well at all. So this is how far I move, about equal to line. Sorry about that. And this right. So in some ways, that's what's going to give us some of the words in later sections where we talk about conservative. So this isn't necessarily a gravity field, so it's not necessarily true here. So I shouldn't in some ways say work in this case, but just to get the idea of what's going on. So this first part is the force at a particular value of t. And again, if I'm not changing t by very much, then I can assume that is basically a constant. So, and then I'll add up all the little pieces. So the usual integral derivative thing is I break up the path into lots of little pieces, find the force at a point, multiplied by how far I move, which I can assume that short distance, I can assume the force is constant and the direction I move is a line. And then take the dot product to get the work of that little tiny piece, and then add it up over all the little tiny pieces. So if we think of it as work, you can see exactly what's going on here, which is just we're taking the dot product of the force and the distance, as we usually do, and then adding them up over all the little pieces. So this is what's going on with line integrals. And as I said, it's easy to think of this as a work, but it would apply to other types of things. So obviously we expect to get back a number. And fortunately I didn't give myself enough room to do it here, but we would get, I think when I do it, I got 24. So in some ways, Jacob leads me into the next thing, which is, so here, for a general vector field, if I take a different path from where I start to where I end, we might get a different answer. We'll find out in the next section that if the vector field is conservative, then it's not going to matter which path I take. So that's what conservative will give us. It'll tell us that the path we take doesn't matter. But in general, if it's not conservative, then it's not necessarily true. So if we follow the same path but with a different parameterization, that does not change. I'll say in a second what that would mean. Right, just something like that. So that's where the term comes from the actual gravity and so on. So let me talk about the second one, because the second one isn't necessarily obvious. So here, in the last one, I'm following along the path y equals x squared plus x, and we did the parameterization t. So here we had that. Well, there's no reason I have to call it t. Suppose I called it t, 2t. And that would be 2t quantity squared, which is 4t squared, plus t, which is 2t. So these are the same paths, the only is, in some sense, the second one is moving along at twice as fast. But that's not going to matter for work, so these will give us the same answer. The only difference is that, of course, this one is t equals 0 to 2, 0. Whereas this would be starting still at 0, but t equals 1. It's supposed to be a 1. Sorry about that. 1. Okay. So the path we take might change things if it's not conservative, which we'll find out in the next section. But the parameterization we use does not matter, as long as it's the same path. So in another kind of more, in a bigger one, if we're going along a circle, if I go from 1, 0 to negative 1, 0 along the circle of radius 1, if I use t comma square root of 1 minus t squared versus cosine of t comma sine of t, is not going to matter. Okay, so let me do another one, and this time see if I can fit it. Oh, sorry. So let me write this again. This is 2. Because we're going from the 0.00 to the 0.26. So in the second one, if I put in t equals 1, I get 26. Yes. So you can see all I've done is put in a 2t instead of a t. So y in terms of x is the same. In both cases, y is equal to x squared plus 2x squared plus x, t squared plus t. Sorry about that. And in both cases, if I go from the first one at 0, I'm at the 0.00. And if I put in 2, I get 26. In the second one, if I put in 0, I get 0, 0. If I put in 1, I get 26. So they're both y is equal to x squared plus x. And they both go from the 0.00 to the 0.26. So it's the same path. So the idea is the parameterization that you use doesn't matter, but the path you take might. So for example, here we have 0, 0 to 26. If instead I'd said we're going to use y is equal to 3x, so a different path, then I might get something different. So in the one we use, this is the path we used. If I changed it to this path, I might get a different number, depending on if it's conservative or not. So any other questions on this before I do one more example? Okay. I'll leave off. Make it simpler. Yeah, sorry. Not sure why I'm having trouble just making up one. And let's just make up one. This one I've already given you the parameterization, although I have no idea what this represents. I'm not sure what type of path it looks like, but that's okay. But also just to show that this works whether we're in 2 or 3 or however many dimensions. 3. So the usual, yeah, it doesn't like my 3s. Although it did the second time. So we have to do the 2 things. First, we have to plug the parameterization into the function. So wherever I see an x, I put in x, t squared. Wherever I see a y, I put in the y. y and z. So the function with the parameterization. Take the derivative of the parameterization. Oops. Should be a 1, of course. And I tell you from 0 to 3, so 0 to 3. And then the dot product, I'll simplify this one. It's t squared, t cubed plus t squared. That's a cubed. And 3 t to the 4th plus 3t cubed, dotted with the 2t 1, 3. And then just do the usual dot product, so the 2t and the t squared, and you're going to double check me here to make sure I'm getting the same thing. So t cubed, the dot product of 1 with the second one, and then the dot product of 3 with the third one. You can see I just get a integral with one variable. I can combine them, so I have 2t and 1 and 9, so 12t cubed. I'm not doing this in order, but I guess that's okay. And it's a fairly large number. And you should not necessarily believe that number, but get the idea. Yes, from here. Right, so that comes from here. Yeah, again, I really just should write slower because it's smoothing out my lines, which sometimes changes them. So now give me a second. Okay, so let me do one more. Sorry about that. A fairly basic one. Actually, let's do a couple paths here. This is to make it a bit more clear that this is okay as long as it's piecewise smooth. So the fact that it's a corner at the point here, and I have to make this more explicit so you know what this actually is. So this is a circle of radius 1 centered at the origin. And so what I'm going to do is I'm going to start at 1, 0. I'm going to move along the circle counterclockwise to the point 0, 1. And then from 0, 1, I'm going to move to the origin. And I want to find the line integral along that curve of this vector field. So the first little thing is a little note. It's just like most integrals. I can split things up. So if I have a path with pieces, I can split it up into the pieces. And while I'm writing notes, I might as well write the other one. If I move along a path in the opposite direction, I get the line integral negative with the line integral in the positive direction. So if I move along a path in one direction, I get the negative if I move along a path in the other direction, which again, if you think of work, makes sense, which is if I push one way, I get the negative work if I push it the opposite way. So for this one, we're going to have to split up into two pieces. And these are the two types that you should be able to get besides the really basic parameterization. Should know, because we've done both of them. So for C1, which is the circle of radius 1, what would be a parameterization for that? Right, so just the polar coordinates. The little thing is here is instead of the r cosine theta, r sine theta, is since we know it's a circle of radius 1, we know r is 1, and I'll just call it t instead of theta just to make it nicer. And so we would get that. So that would be our parameterization. And now we just have to say for what values of t. So at 1, 0, so what are the limits for t? So we start at 0, and we end at, again, pretty obviously, pi over 2. Yep. So otherwise, we do it just like the last one, which is now that we have the parameterization, we plug that into our vector field. So we have x squared, so we have cosine squared of t, and then xy, which is sine of t cosine of t. And since I just made it up, this probably will not be an integral we can do. Take the derivative of the parameterization, which is negative sine of t and cosine of t. And therefore, we get the integral from 0 to pi over 2 of the dot product. Okay, I said probably we can't do, but we can, because what's a dot product? Zero. Yeah. Happens when I make stuff up. So zero is fine. So any work in some sense that we do, it must be negated. So some place it must be positive and some place it must be negative. C2, the other type that you should be able to always get a parameterization. So you should be able to get parameterization for circles because it's just polar coordinates where r is fixed. The other type is lines. And we can do this in two ways. We can use the chapter 1 thing, which is I know if I have the 2 points, one of the ways I can get the equation of the line is I can get the vector from the first point to the second point, and then the line is equal to the point plus t times the second times the vector that's parallel. So I could do that. Or here, it's probably easier to just read off, which is, so here we're going from 0, 1 to 0, 0. So let's start with the easy one. What is x? So x is just 0, so I don't really have to use the full equation. And now for y, I can do a couple things. So one of the things I could do is, well, I'm starting at 1 and I go to 0, so I could say, well, that is 1 minus t. T is 0 to 1. Or I could do to 0 and t. In that case, t would go from 1 to 0. So it looks a little weird in the integral because this would be the integral from 1 to 0 instead of the usual notation where we start with the smaller and go up to the larger. But there's no reason we can't. So as is usually the case, there are a few possible parameterizations that we could use, and any of them are okay. And so because it's easier, and let's see if I can fit this in the margins. Sorry about that. So this is really a fairly easy one, so I might actually be able to fit it up here. So we have the 2 pieces. So the first is we want to put this parameterization into our function. So x is 0, so I get 0. And all right, so this is even shorter than I thought. This is not a good one. Oh, so just, I know I'm going from 0, 1. So I know because of the 2 points I'm at. I'm going to start at 0, 1. So to get 0, 1, I have to plug in t equals 1. And to get 0, 0, I have to plug in t equals 0. So just look at where we start and where we end up. Because now direction does matter. So this is a really boring example. So I plug that in. I take the derivative of this, which is just 0, 1. And so I get the integral from 1 to 0 of 0 dt, which is also 0. So this whole thing is 0. So it happens when I make up something. Everything becomes 0. So same thing. I do the 2 pieces. I plug the parameterization into my vector field. I take the derivative of the vector field. I then take the dot product of those 2 vectors and look at the. In this case, everything becomes 0. Okay. Any questions on this? Okay, so let's do this by itself. I want the line that goes from the point 1, to the point 2, 3. So I said, but let's actually do, which is we want to get the equation of line. So let's go back to chapter 1. What are the 2 steps to get the equation of the line between those 2 points? First step is and then I'll go back and do the 0, 1, 0, 0. Right, so figure out the equivalent of the slope, which is the displacement vector. So if I call this A and B, I would get the vector from A to B, which is, in this case, we do care about the order of the points because direction matters. In chapter 1, we usually didn't care about the direction, so we didn't care what came first. Here, we definitely want to subtract A from B because we're going from A to B. So that will give us the vector 1, 2. And then we get, then the line is, and again here, matters to some extent, we want to put the point we start with first, and then t times the vector. And therefore the parameterization would be just put it into the x variable by itself, 1 plus 1 times t, and then 1 plus 2 times t. So that would be the parameterization. So that always works. And I had, like the last one, I'm going from 0, 1 to 0, 0. If I follow the same thing, which I'm going from A to B, and notice this is t equals 0 to t equals 1, because t gives us the point we start with. And if I put in t equals 1, I get the point I end with. So if I do the same thing here, AB would be 0 minus 0, so 0, and 0 minus 1, so I get the vector is 0, the displacement vector is 0, negative 1. And therefore xy equal to the point I start with. And I get this version of it. And again, t is equal to 0 to 1. So if I use this method, the nice thing is I'm always going from 0 to 1 if it's a line. And it always works. It just might not be the simplest version. Because now I'm getting this 1 minus t. So for example, if I have to square it, it becomes more complicated than the other version I had was just 0t, where I went from 1 to 0. So it would be slightly simpler. So this isn't necessarily giving the simplest form of the line, but it always works and it always gives us the limits from 0 to 1. So any questions on this? Okay. So obviously we have to do more. So start looking through the homework. This is 4.2. So I said 4.1 is really kind of intro, so you don't really need the homework yet. So really look at the homework for 3.11, start working your way through 4.2. And then otherwise, so actually we're a little ahead today, so just the usual quick one into the next section, but we'll finish a little bit early. right, so this is the idea into 4.3. So this is just asking, is this conservative? And then tomorrow we'll talk about what conservative gets us. It'll make things nice. And what we have to do to use the fact that it's conservative to make it nice. So for now, let's just ask if it's conservative. And let me remind you, not sure why I made that one word. There is a function f so that the gradient of that function is equal to what we have here. And what we're going to do right now is just a quick check. Can we check quickly to see if it is? So let me ask, if this is true, so if this is true, then what does this first entry have to be in terms of little f? Oh, so you're actually getting ahead of me, which is we can take the antiderivative, see what it should be, but what I'm looking for is that this thing needs to be the derivative with respect to x. So Kenyon actually is looking into what we're going to do next, which is once we decide it's conservative, we might want to know what is the little function f. Right now, we're just checking. And what is true about the second entry? Right, that must be the derivative with respect to y. Well, we now have this idea, which is what's true about these two. They're equal. So if I call this P and this Q, if this is the gradient of a function, then the derivative of P with respect to y should be equal to the derivative of Q with respect to x. So in other words, I don't have to take the antiderivatives to check. I can just take derivatives. So let's check. What's the derivative of P with respect to y? X. And derivative of Q with respect to x is 2x. They are equal. And that says that this is a conservative vector field. And then our next step would be, now that we know it's conservative, is what is the actual function f? What is the potential function? And then the real question is, why do we care? So that's what we'll get into tomorrow. So usually I go right to the end. Today we have like 14 minutes, because usually in the middle we'd have a worksheet where I'd have maybe do one of these problems, but since we didn't have class yesterday, I wanted to get further along. So this obviously is not on the quiz. So there's a quiz on Thursday. Yeah, so it should be two words. For some reason, I combined them. So there is an f so that the gradient of f is equal to the vector field f. So pretty much the quiz will be short. There'll be one question from the 3.11. Just here's a parameterization, find the, or set out the integral for finding the surface area over a particular region. And the other is like our first example from 4.2. So in theory, stuff from 4.1 could be on it, but as I said, that's really not used yet. So for example, we don't use curl until 4.7, I think. So it's silly to have a quiz on it. So the two things that could be on the quiz are a surface area question from 3.11 and a line integral question from 4.2. And that's what we'll start with tomorrow, is we'll just do 2 or 3 examples from each section. Because we haven't done it for too long, I would probably give you the parameterization. Okay. So as usual, I'm going to stop recording, but if you have questions, stick around. Otherwise, I'll see you tomorrow.